In our introduction to quantum physics, we saw the first instance of how classical physics was not sufficient when talking about the atomic world, things at very small scale. Namely, we saw how the black body radiation could not be explained completely on the basis of classical physics. So the German physicist Max Planck was able to come up with a model which explained the exact shape of black body radiation spectrum. And basically his model said that atoms and molecules oscillate or vibrate like a harmonic oscillator, but they can only vibrate or oscillate at certain discrete frequencies, not at continuous frequencies. And as they do that, they can also emit or absorb energy also in a discrete form. So that quantization of energy is given by this equation, that the energy of an atomic oscillator is equal to some integer n plus 1/2 times Planck's constant h times the frequency of the oscillator, the frequency at which the atom is oscillating. In this video, we look at a second instance of how quantization was necessary to give an adequate and accurate description of reality. And this one involves what's called the photoelectric effect. Photoelectric effect basically is the phenomenon in which when you shine light on a metallic surface, then the energy of that light is absorbed by the metal, and as a result, electrons are ejected from the body of that metal. So the ejection of electrons from such materials when struck by light or other electromagnetic radiation is called photoelectric effect. This is a simple setup typically used to observe photoelectric effect. So basically on the left side, you see a plate here that's a metal, made of a metal, and then light is incident on this piece of metal. On the right side, you see another plate, and these two plates are connected to a battery. The voltage of the battery is called the retarding potential, and you'll see in a minute why. So the metal itself is kept at a higher potential relative to the other plate. So the electrons which are ejected from this metal have a certain amount of kinetic energy, and as a result, they try to go towards the right. But since this plate has a lower potential, it's negative relative to this, these electrons are not welcome, they are repelled by this plate here. So only the most energetic of these photoelectrons, these are called photoelectrons, electrons that are ejected as a result of photoelectric effect. So the photoelectrons are repelled by the negative potential here. So only the most energetic of the photoelectrons can make it to the other side. And because this potential difference has the effect of discouraging or retarding the flow of photoelectrons, that's why this is called the retarding potential. So the ejected electrons are called photoelectrons, and typically photoelectrons that are ejected have some amount of kinetic energy, which helps them overcome the retarding potential and generate a photocurrent. So if these electrons are able to make it to the other side, then you have a circuit in which you have a current flowing, which is called the photocurrent. Now, if you keep increasing the retarding potential, then it becomes more and more discouraging for the electrons, for the photoelectrons to cross this potential barrier. And eventually you'll reach a point where the photocurrent drops to zero. It becomes zero. So the retarding potential at which the photocurrent becomes exactly zero, basically what that means is at that retarding potential, at that threshold, at that verge, at that boundary, uh, only the most energetic of the photoelectrons with maximum kinetic energy, Ke max, are the ones which are able to make it. So when the retarding potential is equal to the kinetic energy of the most energetic electrons, that's when the photocurrent becomes zero. So let's take, for an example, if current becomes zero, photocurrent becomes zero when the retarding potential is 5 volts. So what that tells us is that the kinetic energy of the most energetic photoelectrons was 5 electron volts, which can be converted to SI units to joules by multiplying with the conversion factor 1.6 times 10 to the negative 19. Now, the nature of photoelectric effect led Einstein to conclude that light was behaving as a stream of particles rather than a wave. So up until that time, the common understanding of light was that it's made up of waves. But because of the observations in photoelectric effect, Einstein concluded that that is not the case. Actually, light is made of a stream of particles. When light interacts with electrons in the target of the photoelectric effect of the target material, some of the energy of the light goes into overcoming the barrier that keeps the electrons bound to the material. So typically we're talking about free electrons and they're confined to the body of the metal. So there's a certain barrier which keeps them confined to the body of the metal. So the light that you're shining, some of the energy of that light goes into overcoming the barrier. And then whatever is left over, whatever energy is left over, is the kinetic energy of the photoelectrons. So rest of the energy after having overcome the barrier is the kinetic energy of the photoelectrons. Binding energy is the term used for energy that keeps the electrons in the body of the metal, or it's the energy needed to overcome the barrier. Binding energy is also sometimes known as work function. Now, what is it about photoelectric effect that led Einstein to conclude light was behaving as particles rather than waves? First of all, energy of a wave, like light, is related to its intensity. If you double the intensity, the energy would double. And if light was wave, then by increasing its intensity high enough, photoelectrons could be produced. So it was just a matter of getting to the right intensity if you wanted to see photoelectrons being produced. But what was actually observed was not that. What was found experimentally was that it wasn't a minimum intensity of light that was needed, it was a minimum frequency of light that was needed. And that minimum frequency at which photoelectric effect is observed for a given metal is called its threshold frequency F naught. So that was one clue that light was actually behaving not like a wave. Uh, Second point in this regard, photoelectrons are ejected immediately after light hits the target. So as long as the frequency of the light is above the threshold frequency, as soon as light falls on the metal, you observe photoelectrons being emitted. If, however, light was a wave instead of a particle, then there would be some time lapse between when the light starts shining and the photoelectrons being ejected. Because you're trying to, if it was a wave, you have to have sufficient energy which needs to be accumulated before photoelectrons would be observed. But because that observation is pretty much instantaneous, it is concluded that uh, the light is made up of particles which go in to the metal like a billiard ball and knock off the photoelectrons from the body of the metal. So when particles collide, energy is transferred instantaneously, and that is how you see instantaneous emission of photoelectrons. So these observations led Einstein to conclude that in the context of photoelectric effect, light behaved like particles or discrete packets of energy, which are called photons. Taking his lead from Planck's quantization of atomic oscillators, Einstein proposed that the energy of each photon is given by this equation, E equals a multiple, Planck's constant times the frequency. So the multiplying factor of the frequency was the Planck's constant. This would also enable Planck's blackbody oscillators to increase or decrease in energy by multiples of hf rather than in a continuous fashion. So it has to be 1 hf or 2 hf or 3 hf, but nothing in between, because you can only have either one photon of this energy or two photons or three photons, but not 2.5. So that sort of also strengthened Planck's model of atomic oscillations. So the energy of the oscillator increases or decreases in multiples of hf by absorbing or emitting certain number of such photons. 1, 2, 3. So 1 hf energy or 2 hf energy or 3 hf energy is either absorbed or emitted by the atoms. Now, the intensity of electromagnetic radiation is related to number of photons. So when you increase the intensity, you're not increasing the energy, but you're just increasing the number of photons. You're not increasing the energy of each photon, but what you're affecting is the number. So some of the photon energy, which is hf, goes into overcoming the binding energy, as I was saying earlier, and the rest is the kinetic energy of the photoelectrons. So if you consider one photon entering the metal and hitting an electron, then the energy of that photon, hf, some of it goes into overcoming the barrier, which is the binding energy, and the rest is the kinetic energy of the photoelectron that's emitted. So from this, you can say Ke of the electron is hf minus the binding energy. And for the maximum kinetic energy, the most energetic photoelectron, the binding energy would be hf naught, where f naught is the threshold frequency. Now, if you make a graph of the kinetic energy of the photoelectrons as a function of frequency, as you would expect from this equation, kinetic energy of the electrons as a function of frequency. It's a linear function, and that with a positive slope, and that's what you see here. If you're plotting Ke versus F, you expect the slope to be h, the Planck's constant. And in fact, this graph is used to, that's one of the ways in which you can have a measurement of Planck's constant. So you basically look at the kinetic energy as a function of frequency, draw the graph, and the slope gives you the Planck's constant. The x-intercept of this graph, which is indicated by F naught here, would be the threshold frequency, meaning if the frequency of the photons is less than the threshold frequency, there will be no photoelectrons, so there will be no kinetic energy to talk about. Okay, let's look at problem number 7. So the problem says, calculate the binding energy in electron volts of electrons in aluminum if the longest wavelength photon that can eject them is 304 nanometers. So the binding energy I was talking about is characteristic of the metal of which the target is made. So different metals have different value of binding energy, meaning that free electrons are more tightly bound or less tightly bound inside the body of the metal, depending on what the material is. So in this problem, we have to calculate the binding energy. So BE is what we're looking for. We were given that the threshold wavelength, not threshold frequency, but threshold wavelength is 304 nanometers, or when you convert it to SI units, 304 times 10 to the negative 9 meters. So using the equation that we had for involving binding energy being equal to HF naught, BE equals HF naught, but we want lambda naught because we know the threshold wavelength, not threshold frequency. So using the equation, frequency is speed divided by wavelength. Binding energy is simply hc over lambda naught. And then you plug in the values, Planck's constant here, speed of light, 3 times 10 raised to 8. Lambda naught is 304 times 10 to the negative 9. Now, this would give you binding energy in joules. Since we want our answer in electron volts, we divide that by 1.6 times 10 to the negative 19, the conversion factor, electronic charge. And this comes out to 4.01 electron volts.